about Chapter 2, Section 4, chemical reactions and enzymes. And so just to think about it before we begin, that all living things are made up of chemical compounds going from monomers to polymers, and everything that happens in our body, growing, interacting, and responding to our environment, reproducing, metabolism, digesting food, all stems and bases off of chemical reactions.
So when we're talking about chemical reactions, really what we're concerned with is the energy, and particularly the energy that's stored in the bonds between different atoms. Energy just in general, as you can read here, is the ability to move or change matter. It takes on different forms. You can all think of the heat you felt, light, chemical, mechanical, and electrical. We will most particularly be talking about chemical energy today, as that's usually what living things, particularly consumers, use. It can be stored or released. Energy can be in chemical reactions. Remember, that's the bonds.
Okay, so when talking with chemical reactions, we're bringing back some more of the physical science that you should learn, that you should have learned back in 9th grade or back in junior high, but the process that changes or transfers one set of chemicals. So we look at a chemical reaction as an example. You need to know these vocabulary words, the reactants and products of what a chemical reaction is entailing. And basically it's changing, and like Yasichek said about bonds joining and breaking to form different formulas, different molecules rearranging themselves. And so the left side is what we call the reactant. So the left side of the arrow, this is the reactants. These are the chemicals going into a chemical reaction. And then the right side is what we call the products. Products is what is produced, what is the outcome of the end of what is the reaction that has occurred.
And notice we have the same atoms on both sides, just rearranged in different forms. So you have carbons on the reactant side, you also have to have carbon on the product side. So remember, again, here we're talking about the bonds between these things changing is really what a chemical reaction is.
Okay, so energy is absorbed when you have the bonds together. When carbon and hydrogen are bonded together, they are storing energy. And when the bonds are broken, when these chemical bonds are broken, that's when you're releasing out energy. So the forming of bonds, the breaking of bonds, that's all absorbing and releasing energy. So some examples in our body, for example, of chemical reactions occurring would be metabolism. When we are digesting our food, these chemical reactions occur. When we have digestion, when we, for example, proteins, when we eat meat, we break the chains of amino acids, the enzymes that we have inside of our bodies. They break down into amino acids, and so this energy is released from the breaking down of foods, from these chemical reactions, breaking bonds and releasing that energy.
So remember, monomers are built into polymers, usually as a form of a way to store energy. So glucose is built into a starch, and then when you need to access that energy, you want to break the bonds in starch back down into glucose, and in so doing, you're releasing the energy held in those bonds. Okay, active ocean energy is an important concept, particularly when we're dealing with enzymes, but it takes place anywhere in chemistry. Anytime you have a reaction taking place, you have the potential for the need for energy to be added to the reaction, a little bit of energy to be added to the reaction before it can work. So easy way to think about this, right? If you've ever had a campfire before, you know you can sit and stare at it all day long. You can have all the wood you need, all the paper there, you can have good air movement, and you're not going to have a fire, right? You need to add a little bit of energy in the form of a match, right? So a match would be like the activation energy for that. And once, of course, it gets going, you've gotten over that hump, so to speak. Now you have combustion, right? You have that reaction taking place.
So these are just two types of graphs showing energy, a reaction that's absorbing energy, and then you have a chemical reaction showing energy being released, and it's showing the amount of activation energy needed to get the reaction to go, to get it started, to get it moving. So what are enzymes? Enzymes are really important, and they're actually specialized proteins. Enzymes are proteins made of amino acids. And so why are enzymes important, or what they do? They help speed up chemical reactions, which helps maintain homeostasis. And without enzymes, you would not be able to have chemical reactions occurring in our body quick enough, and so we wouldn't basically be able to stay alive.
So the whole purpose of an enzyme is really to, referring back to that activation energy we talked about, is to really lower that energy needed. Another way to think about this sort of metaphorically is imagine you have a nut that you need to turn out, right? And if you tried to do that with your hand, you might be able to make it happen, but it's a very difficult, very time-consuming process. If you had a wrench, right, you could make that happen much quicker. Enzymes are like the wrench. They're there, they help speed up a process, thereby lowering the activation energy required for that process to take place.
So this is an enzyme activation energy graph. So if you look at the red line, this is showing how, if you're using a chemical reaction, you have the reactants. Right here, the reaction occurs, and this is your products at the end. And this red one is showing if you were to use an enzyme and how much activation energy is needed, how much energy is needed to get that reaction started. There is not very much. When you look at the blue line, this blue line is using without an enzyme, what it takes to not have an enzyme help. And so if you look at the type of activation energy, it's a whole lot more energy needed to get the reaction started. To get the reaction to go from reactants to products, you need a whole lot more energy. So it's really important to use enzymes because it lowers how much energy is needed to get the reaction started.
So reactions will take place no matter what, but they often will go much slower than needed or wanted, much less efficiently without enzymes.
Okay, so how do enzymes do their job? Enzymes provide a place for reactants to occur. So there's what we call this enzyme substrates situation. So what happens is the reactants bind to the enzyme. And this whole process is called a substrate. And the substrate then binds to this active site on the enzyme, where you're able to make this lock and key fit situation. And so if you look down here at this picture, this is the enzyme, okay? Right here is this activation site where the reactant comes in. When the reactant comes in, this is what we call an enzyme substrate complex, where all of this fits together, and then the chemical reaction can happen a lot faster. And so here is another visual showing you that this is an enzyme. Water and carbon dioxide come in to the activation site. We make this substrate complex. The chemical reaction breaking and reforming of bonds till we make carbonic acid. Okay? Now here's something really important about enzymes. This specific enzyme will only work with this reactants, this substrate.
Another important point that maybe we haven't mentioned to this juncture yet about enzymes is maybe you can see here is that it is not used up. Okay? Enzymes are catalysts, and by definition, that is something that can play a role in a chemical reaction, but it is not used up. It's not a product, it's not a reactant, it sort of speeds up the arrow, so to speak. And it's not used up. Again, to go back to the wrench metaphor, right? You can use that wrench over and over and over again to turn many bolts over time, but the wrench itself is unchanged by that.
Right. So again, one more visual to show you. This is the enzyme. This is the activation site. The substrate, or the reactant. This is also called a reactant. Okay, this reactant comes in and fits perfectly like a lock and key. Then the chemical reaction happens, the two products come, but look, the enzyme shape has not changed. We can go back and reuse it again.
And again, you can see here your substrate would and could break into its two parts over time, but it takes energy to do that, and the enzyme has lowered that energy needed to make that happen, thus making it happen more quickly, more readily.
All right, and that is